Thanks very much, Tim. I think the only qualification that I would put on Tim's kind introduction is that his role in both reports has been more than minor, and thanks very much for that. And I've no idea where 10 years has gone, and quite where the next 10 years will go is quite a terrifying thought. So I won't talk for a huge length of time, probably 20 minutes or half an hour to give you a flavour of the report. I'm aware that we've got a rather different audience from the one that we had yesterday morning when we were with a group of journalists. I'm looking around at some of the more distinguished professors of electrical engineering in the room with some trepidation. But I'm very much looking forward to the opportunity to both present and discuss what we've tried to do with this particular report for UKERC. Is this show? Yes, okay. So what we're going to do is just take you through a little bit of context to the report, some of the background and the research approach that we used. In this report, we used this approach of systematic review, which we developed in 2006. We used it for the first time for UKERC those years ago. And I think we've done something like 12 or more, 12 or 15 other reports in the intervening period, but the approach of systematic review is the one that we've sustained throughout. Talk about exactly how we went, what we asked ourselves for this particular piece of work, recap how we saw the world in 2006, and then take you through some of our findings, some of the graphs that we've put together of those findings, and then conclude. In 2006, we thought that 20% of electricity from renewables would be really going some. We thought that would be pretty ambitious. And yet many countries have already reached that kind of level. I think it's of the order of 13 or 15% from variable renewables in the UK, and around about 20% from all renewables in the UK already. And similar levels have been reached in Denmark, in Germany, in Ireland, Spain, and a number of other places. So the world's really moved on. We've done what we did previously, which is to interrogate various literatures. This is a meta-analysis rather than primary modelling or primary evidence gathering. And as you can see, we go through a process that involves lots of consultation, peer review, and all of those good things. What we asked, rather a wordy slide, we were asking specifically about what new evidence had come to light since we reported on this topic in 2006. And we asked whether or not the range of impacts or the things that people are concerned about with regards to renewables integration had changed or expanded, whether there were new categories of interest, new things that were in focus. And we were also keen to understand as to, we did this back in 2006 because it was extremely contested at the time, highly controversial. Renewables intermittency is a huge problem, says one group of people. It will cause the lights to go out and hold back renewables. It's no problem at all, says another group of people. And at that time were able to build some consensus within our expert group, which had a range of views. So we're also keen to understand the extent to which this continues to be a focus of controversy or whether consensus has improved. Because we did this meta-analysis and brought together whatever it was at that time, 100 plus studies and a whole bunch of data that went from Finland to Australia to the United States, we had a lot of impact with this report. It was very widely cited at the time by government departments, select committees, and so on. And we found at that time that there were two main categories of impact. We didn't discuss at length some of the other categories of impact, which I'll come back to. And we did a rather simple job of adding together short-term system balancing, short-term operating reserve costs, and the costs of providing capacity across peaks. And we came to the conclusion that in 2006 costs, it was around about £5 to £8 per megawatt hour on the UK system, mainly for wind. Obviously there's various qualifications and caveats and around that. Phil has very helpfully inflated those figures and put it in small font at the bottom of the slide. Inflation hasn't been that significant in the last 10 years, so the difference is not that huge. We're still talking about, in today's prices, around about £10 per megawatt hour. Now I'm going to come back to that figure, and I'm going to come back because it's bandied around in the wider conversation to date, and it's interesting to think about and to discuss whether or not our more recent findings are consistent with that kind of level of impact as we look beyond 20%. So we found a lot more data in the previous 10 years or so. More people alive today than were ever alive before, or whatever the statistic is. There's a similar statistic for the intermittency literature. There has been more new analyses, more modelling, more data are available on intermittency for the period from 2006 to date than we found for the preceding kind of 3 decades worth of research into this topic. And you can see a whole bunch of other stuff about how many 200s or 2000s or other numbers starting with 2 we were able to find between 2006 and 2016. And what we've also done, so just to be clear, this isn't a breakdown of costs, this isn't a share of total costs, this is a report of the data that are available on intermittency, and it provides you with a picture of what kinds of categories of impact the literature has been concerning itself with in the data that we found through our review. So there is an overwhelming amount of, majority of the data is discussing capacity credit, for example. But not just that, and there's a whole bunch of other things that you can see in the graph as well. Another important aspect of this discussion is it was never an easy topic. I think we always found when we were discussing this on the media, or if we were engaging with policymakers or certainly non-specialist sort of politicians, select committees, the devil always had all the best tunes on this. It was much easier to tell a simple and negative story about the costs of intermittency than it was to explain to a lay audience the complexity of all of the wide-ranging system costs that might be imposed by renewables, how those differ from what might be imposed by other categories of technology, and so on. But I think it's become even more important and even more apparent that oversimplification is not the way to go. Back of a fag packet type approaches have got all sorts of advantages in all sorts of domains, but are unlikely to be particularly helpful if you're concerned with assessing the system impacts of changing the mix of generation, possibly changing the nature of demand and levels of interconnection, and all sorts of other complex and interrelated things that affect how much a system of electricity generation and supply costs to operate and to keep secure. It's also very important to note we will take you through some of our findings on a number of separate categories of cost. But it is important to be clear that what you can't do, or at least won't get the right answer if you try to do, is in a very simplistic fashion add all of those costs together and say that that's what the system costs of renewables must add up to, because there's a great deal of interaction and overlap and interrelationship between all of these impacts, which takes me back to this important point that the slide kind of opens up with. that you need to look at this using the kind of modelling and simulation, power system simulation approach that I know that colleagues in the room are able to do and are experts in, if you are to get an accurate kind of understanding of variable renewables on the system. Despite that, there is a large amount of literature out there that does report these individual cost impacts. I know that these individual cost impacts are of interest in policymaking circles at the moment. They're discussed in a forthcoming Select Committee report, which I think is going to hit the front pages on Friday, for example, on the economics of energy. And so what we've done in the report is to take the reader through some of these categories, explain them, present the range of findings, and I'm going to do that in the slides that follow with some of the data that we found. So we've got a few slides now that provide some of these data ranges and provide a bit of kind of explanation and exposition around what we found, our interpretation of it, and what we think it all means before we go on to conclude. So the first category of impact which I'm presenting findings for is short-term system balancing reserve costs. And this effectively are the system services which, in this country, the system operator is National Grid. National Grid will tender for a bunch of system services which it can call on in extremis to come into operation over a range of relatively short timescales. In fact, from the kind of very short indeed frequency response through to a number of hours in order to ensure that demand matches supply on an instantaneous basis. Now, much of that demand-supply balancing is managed through the marketplace without intervention, but the extent to which short-term system balancing reserve costs change when you have variable renewables on the system is something which many analyses seek to quantify. And so we're reporting this range in the slide. Now, there's a number of things we can observe about this. The first is that there's a good set of data up to about 30%. So this is by energy. So this is the amount of annual energy that's met by variable renewable sources. And there's a good degree of agreement that that up to this level, the majority of results are below £5 per megawatt hour, and you can see that very clearly on the slide. And what we also discuss in the report is this doesn't represent a hockey stick. This isn't a kind of J-curve. These are simply the data that we found. And that's extremely important, and I would emphasise that. So at this 50% level, there's a family, in fact, of studies, a cluster of research that was undertaken, I think I'm right in saying, by a certain professor who's in the room, using a simulation model to test sensitivity to system flexibility. And that gives a range of between £15 and £45 per megawatt hour. And so just what's going on? Well, as I've said, these results explore the range of flexibility and different mixes of plants. So I'm going to come back to this point because it's a theme that we have tried to develop in the report, which is there isn't a single answer. You can see that from the first slide. But the reason that there isn't a single answer is not that nobody can agree about this or nobody can agree how to approach doing this. It's because the contextual factors about the nature of the renewable resource, the nature of the demand, and the nature of the balance of plant affect the size of this cost. And that's, I think, one of the most important things which we are keen to get across in presenting this report to policymakers and others. So this is looking at the costs of ensuring that you can reliably meet peak demand. So this is another category of impact. Now this is quite a, sorry Phil, this is a particularly ugly slide, and the reason that this is a particularly ugly slide is because you've got that blue line that goes off below the horizontal axes and goes quite strongly negative. The reason that some of the data go quite strongly negative is because it's perfectly possible for the output from renewables to be strongly positively correlated with peak demand, which means that, for example, in an air conditioning driven solar hot sunny country with lots of solar energy, that it could be making a positive contribution to system reliability, and that's what you can see in that particular slide. But again, what we wanted to do was to give an illustration in the slide pack of what might be most relevant to the UK context, and so we've highlighted where wind analyses dominate and where the demand and supply conditions in the various studies are broadly consistent with UK conditions. The most results lie in the range of £4 to £7 per megawatt hour. Almost all the results are less than £15 per megawatt hour. And this is really important to emphasise, because for this particular category of impact, you can assume that the contribution to peak reliability is zero. So, for example, solar provides zero contribution to capacity credit in the UK environment, because it's always dark at 5 o'clock on a January evening, which is when peak demands occur. And you can run the analysis to assess what it costs to ensure that you can still meet peak demands reliably, irrespective of that zero capacity credit. And effectively, the costs reach an asymptotic point. They come to a maximum, even if you're backing up 100% what you need to provide reliable supplies across peaks. And our own analysis, which used a kind of simple representation of this, was broadly consistent with that. We discussed that in our earlier report, and again, this comes to this kind of broadly equivalent figure of £14 per megawatt hour. So I've got a couple of slides now that try and explain some of the sources of this range. So this gives the capacity credit ranges by region, and the next slide gives the same data by category of technology, so split between solar and wind. So obviously you can see there's a direct map across between some of those sunnier locations and some of those lines on the graph which are for PV in those sunnier locations. And it's quite interesting to observe that the results for PV basically cluster around zero capacity credit in countries like the UK, and potentially quite a high capacity credit in some sunnier parts of the world, depending on their demand profile. That's not a given, that's not necessarily the case. It would be wrong to suggest that in all sunny countries peak demand correlates with sunny periods, because it may not. It may be that they've got also an extreme climate and it's cold, and they have a lot of electric heating in the winter when it's not so sunny, or that they have an aircon or a demand peak which is after dark, but nevertheless you can see these results in the data, and these help to explain some of the things which are going on in this graph. Okay. Now, this is a simplification that we've said we won't make, but we've done it on this slide anyway. What we did for our 2006 report was very crudely, really, add together the short-run system balancing costs and the costs of ensuring that you've got capacity across peak. Now, if you do that, and we do say very many times in the report that you really shouldn't, and the reason that you really shouldn't is because it might be double counting the same bits of kit, the same sources of supply, may be providing reliability of supply across peak, and they may be offering short-term system balancing services as well. And disentangling those two things is quite difficult and quite complicated. Nevertheless, we were pressed yesterday morning at our press launch to tell the journalists present what the answer was, which we struggled to do. But the figure of £10 per megawatt hour widely used in the debate. It's been used by the Committee on Climate Change, it's been by DEC, and it's been used in various select committee reports and so on. And it's quite interesting, I think, to observe that it's still consistent with what we find in our data for for a 30% penetration of variable renewables, as opposed to the 20% penetration that we were talking about 10 years ago. And so this is for broadly UK-like wind-dominated systems, but do be very careful about that kind of level of simplification. So this is one of the other categories of impact for which we're able to find significant metadata. And this is curtailment of renewables for a variety of reasons to do with system operation, to do with, for example, ensuring there's enough rotating plant on the system to provide inertia, or to do with transmission or other network constraints. And as you can see, there's quite an interesting and quite diverse range of data that are available. So the first thing to say is that most of the UK relevant analysis suggests that levels of curtailment are very, very low until you get above 50% penetration by energy. And in fact, the data that you can see kind of going up towards 100% curtailment were in fact effectively sort of boundary testing model runs. So in those kinds of examples, renewables were stuffed into the system despite the fact that the system was not able to, was not flexible enough to absorb their energy, until you reached a stage where effectively you were building a megawatt of new capacity, and every kilowatt hour of the output that capacity was able to provide was effectively wasted because the system wasn't able to contain it. So rather than that being an example, if you like, of what could happen, it's really an illustration of what not to do, because that would be irrational in the extreme for policymakers to encourage or system operators to facilitate. So the report takes you through a bunch of other impacts and issues. It discusses transmission and distribution network reinforcement costs, and there's a range available in the literature for that. Now, there's a number of reasons for why we are somewhat cautious about the way that we present those cost findings. The first is they're not, strictly speaking, necessarily an intermittency cost at all. The fact, for example, that solar might be largely embedded is a separate category of impact that has very little to do with the fact that its output varies with the sunlight. Some of those costs are internalised. So, for example, the offshore transmission costs that are imposed upon offshore wind farms feature in the full costs of the project development cycle, and therefore appear in the subsidy that those technologies are provided with. And the second is that large-scale transmission reinforcement, like the bootstrap up to Scotland, for example, provide a wide range, and interconnection into mainland Europe, provide a wide range of benefits which go well beyond intermittency impacts. Nevertheless, they're there in the literature and they're there in our report. There's another couple of impacts which are receiving a considerable amount of discussion in the literature and in the wider policy debate at the moment. The first is the impact on thermal plant efficiency, so the kind of idea that as penetrations of renewables rise, the operation of conventional coal and gas-fired power stations needs to be adapted. The load factors of those plants might be reduced. The cycling of those plants might be increased, and that this will have an impact on their overall operation. And what we found really was that the data on that was quite inconclusive, that there were a number of studies that suggested that the implications of those efficiency impacts were small from a cost and carbon emissions perspective. But nevertheless, there is obviously a real cost there, and we need to be aware of that and thinking about how that's mediated through the marketplace. And there's a second set of conversations that are happening at the moment which is quite prominent in the engineering community around the availability or lack of mechanical inertia on an AC system, and the extent to which that can be accommodated, can be adapted, can be adjusted for using various forms of synthetic inertia and so on. The island of Ireland, for example, is imposing constraints on wind farm operation that are largely designed to ensure there's enough mechanical inertia on the system at certain levels of instantaneous penetrations of wind. But what we didn't find was that this literature had progressed to the stage where there were robust cost estimates available for this particular category of impact. And then finally, we discussed the relationship between costs and prices. So the relationship between the kinds of categories of cost impact that are, if you like, something of an abstraction that we were talking about I was talking about in some of the previous slides, and how well those costs are mediated through the various different designs of electricity market that we have in the world, and the extent to which those costs are cost effectively reflected in markets. And there's some discussion of that as well. And certainly we can see in a number of countries where the penetration of renewables is large, and where the market for where renewables are largely removed from conventional wholesale markets because they're given a guaranteed feed-in tariff or something like that. There have been some quite significant impacts on the operation and the financial feasibility of the balance of plant. Again, that's not something that we can necessarily readily bring into the report and put a number against, because it's much more to do with how cost reflective prices are in markets than to do with what a number or a price or a pounds per megawatt hour figure might be. Okay, so to move to our main conclusions, despite saying that we have to be very, very careful about adding these costs together, if you do take the main UK relevant balancing and reliability costs, these add up to of the order of £10 per megawatt hour. What we've seen, and perhaps I ought to have said something about this as I opened rather than in conclusion, is that 10 years ago, the main subject of conversation was how much it costs to the capital costs of a wind farm, or the capital cost of whatever renewable form of generation there might be, and what that translates to in terms of a levelized cost of energy. And how much higher that was than the least cost conventional equivalent, so gas-fired CCGT, for example. And whilst there was a debate about system costs, we came to the conclusion that system costs were small relative to generation costs. They were 10% or less. What we've seen over the last 10 years, and particularly in the last 5 or 6 years, is very dramatic reductions in costs for LCOE costs. Solar is very often pointed to, but we've certainly seen this emerging in wind, and we've seen internationally an increasing move towards auctions and tenders to set the prices that are given for feed-in tariffs or power purchase agreements for these kinds of technologies, to the extent to which we are certainly seeing a number of technologies in an overlapping cost range at the power station gate or at the wind farm gate, neglecting these system costs. So system costs become a much more important subject of conversation. What we've found through trying to investigate do a meta-analysis and investigate the data on this is the cost ranges that we can point to lie in quite a wide range. What we can also say is that the range is partly, there may be outliers where a particular author has taken a rather unconventional approach, and partly the range will be down to the context and the contingencies. Is demand coincident with sunshine? Are we talking about solar? When is it windy? And all of those kinds of things. But largely, the range is a factor of the flexibility of the system into which we're trying to bring these new renewables. And I think it's straightforward to conclude that the costs for flexible systems are likely to be relatively modest, and that the costs for non-flexible systems are likely to be high. And there's a relationship between the nature of the system that we end up with as we move through the next 10 years, say, since this is 10 years from our previous report, will be a function of the policy environment that's provided and the extent to which flexibility of operation is encouraged, whether that's through flexible gas-fired power station, whether that's through increased interconnection, whether that's through storage, or whether that's through demand-side response. None of those things will be entirely independent of the way that the regulatory environment rewards and incentivizes flexibility. And finally, just on a more methodological note, the kind of whole system analytical approach is essential. You can't oversimplify such a complex problem, and therefore the whole system simulations that we've found do provide the best way to go about thinking about intermittency and understanding the nature of these impacts. I think that's it. Phil will now answer all the difficult questions.